integral. Let's now talk about some of the properties of the definite integral. Our first property is if we integrate from a to a of some function f of x dx, we get 0. Remember that the idea here is that we're finding the area under the curve. What's the area under the curve from the same starting position to the same ending position? Obviously it will be 0. We can prove it by taking an easy example here. What's the definite integral of this? Well, it will be, we have to find the indefinite integral here, which would be x squared divided by 2 plus x from 2 to 2. Well, that means we're going to have to plug in 2. When I plug in 2, I get 2 squared is 4 divided by 2 is 2 plus 2 is 4. So I get 4 minus, when I plug in a 4 again, I get 4, which is equal to 0. So we see that, yes, this rule does hold. Our second rule is if we integrate from a to b of f of x dx, that's the same as the opposite if we switch our lower and upper bounds. If we switch a and b, then we have to take the opposite of our integral. Well, we can prove that by taking a very easy example here. 3x squared dx, first we find the indefinite integral, which would be add and divide. When I add to that exponent and then I divide, I get x to the third over 3. The 3's cancel, and I'll get x to the third evaluated from 1 to 2. That is, plug in a 2 and you get 8. Plug in a 1 and you get 1. 8 minus 1 is 7. So our integral for this from 1 to 2 is 7. If I switch these, I should expect the opposite of that. So this is, again, 3x squared. When I take the integral, I get x cubed, and I'm evaluating that 2 to 1. My lower bound is 2, my upper bound is 1. That means plug in a 1, and I get 1. Plug in a 2, and I get 8. 1 minus 8 is negative 7. So we can see that, yes, indeed, they are opposite each other. Let's now talk about, let's continue on with our properties of the indefinite. Let's now continue with properties of the definite integral. If I'm integrating from a to b of f of x dx, provided, this is the key, where a is less than or equal to c, which is less than or equal to b, in other words, c is somewhere between a and b, then I can split this integral up into the integral of a to c of f of x dx, plus, it's important that the c goes on top here and the c goes on the bottom here, from c to b of f of x dx. It's as if a is New York and c is Chicago and b is LA. You could take a direct flight from New York to LA, or you can go New York, Chicago, Chicago, LA, and you'll get the same distance traveled. For example, if I have the definite integral of 0 to 10 of 3x squared dx, we know that this goes plus 1 divided by 3 gives us x cubed from 0 to 10. Plug in the 10, plug in the 0, and we'll get 1,000. So we know that the area under this curve is 1,000 square units. Well, we can split this up to 0 to 5 and then 5 to 10. For example, this here will again be x cubed from 0 to 5 plus x cubed, I integrated that, from 5 to 10. Well, 5 times 5 times 5 is 125 minus 0, plus, if I plug a 10 in there, I'm going to get 1,000 minus 5 cubed is 125. So I can put that in parentheses there. And this works out to 125 minus 125 plus 1,000 still gives me 1,000. So either way, I'm going to get to my answer, 1,000 square units underneath this curve, if I integrate directly from 0 to 10, or if I split it up, provided 5 is between 0 and 10. Either way, it works out the same. As we continue on with our properties of the definite integral, I should hope that this particular property is of no surprise to anyone. If we're integrating from a to b of k f of x dx, where k is some constant, then we can pull the constant outside of the definite integral to make it k times the integral a to b f of x dx. For example, if I'm integrating 1 to 4 of 12 x cubed dx, this 12 can cause me some problems. So what I'll do is I'll make this equal to 12 times the definite integral 1 to 4 x cubed dx. And then it's just a little bit easier to integrate this. You'd see this is a go to 12 times, usually you include the parentheses like that, 12 times the quantity, this will be x to the 4th over 4 integrated from 1 to 4. And then you can just keep the 12 outside when you plug in the 4 minus plug in the 1, and you'll get your answer. Here is our last property of the definite integral. And again, this one should be no surprise if you've been paying attention during the course. If we have the integral from a to b of f of x plus or minus another function g of x, all integrated with respect to dx, we can split this up into a to b f of x dx plus or minus, whatever the problem calls for, a to b g of x dx. When would you use that? In an example like this. If we're integrating 0 to 3, the definite integral 0 to 3 of 4x cubed plus 3x squared dx. Of course, you can integrate this in one fell swoop. Or you could split this up if you feel more comfortable splitting this up into 0 to 3 of 4x cubed dx. This calls for a plus, so we'll add 0 to 3 of 3x squared dx. Now I can integrate these each separately, and I'd have, if I add and then divide, I'm going to have x to the 4th from 0 to 3 plus, if I add and divide, I'm going to have x cubed from 0 to 3. I could evaluate each of those separately and then combine my answers. Notice it's going to be plug in a 3 minus plug in a 0 plus plug in a 3 minus plug in a 0. It involves a little more addition and subtraction, but I'm sure you can handle that.